So, are you able to see my screen? Yeah. So, before everyone comes, can you just give us some of the introduction? You are from geomatics engineer, like some background you have in that CS background. Okay. So, have you came across this satellite images or something like that before, or working on that? Okay. So, how do you get to know about this course? Okay. Okay, so in CS, do you have like some idea about what you are going to do in your PhD or some tentative research area? Okay, so basically, for 3D mapping, we use drones, lidar sensors, and all those things. One of the things which we know called as a photogrammetry. So taking a picture of images from different perspectives and then creating a 3D model out of it. So that was Yeah, so that was the part of the initial course content of this course. So you just go through the videos. In that, it is mentioned like how you can use those techniques. So basically, if you have any object, you can take the photos from various angles, and then you try to compile all those images into one to make a 3D model. So that technique is known as a photogrammetry. In this course, particularly, how we use it as we have one satellite sensors or aircraft which is going in the sky, and it is taking a picture of terrain from different perspectives or different locations at different angles, and after that we mosaic those images and make a 3D model out of it. So then after in this course we heard about the digital images, how we can work with that, whatever images which we have covered, like taken from this aircraft or satellite sensors. And then there is a content on remote sensing. Basically, if you are taking multiple images from satellite or some other sensors, how we can use and extract information out of those images. So those are the things we have already covered in this course. And further in this course, couple of more things are there, such as we have GPS, which we are going to do today. In addition to GPS, we have lidar, drones, and then after some classes on GIS, and then some on digital image processing. So those contents are remaining now. So I request to just go through the content one more time. It will be helpful for you in for 3D modeling part. Yeah. So those who have joined, hello everyone. Good afternoon. Yeah. So how are you guys? Good, good, good. So have you gone through the videos of GPS of week 6? Yes. So any issues or any difficulties in that? Okay. Anyone else? Do you have any difficulties or any issues in the GPS videos? Okay. So if there is no issue, we will start today's session. So today we have both the things. What do you guys want to do? Should we start questions first, or I will just give a glimpse of topics which we covered in the last week, and then after we'll start the question answer. Okay, so if there is no response, then what I will consider it as we'll start with concepts which we learned. So I will cover few topics which is there in the video and some advance of it, and how this data will look like in actual real life when you get the data from GPS. And then after we will start solving the questions on that part. Okay, so let's get started. So those who don't know me, I am Hiren Solanki, a PhD scholar in Department of Earth Science at IIT Gandhinagar. I am a fourth-year PhD student in the Department of Earth Science and working on machine learning and deep learning techniques in hydrology and how we can incorporate it for inflow prediction and flood predictions. So let's get started with today's content where we are going to discuss about GPS. First of all of you have used GPS in one way or other way through your mobile phones, isn't it? So while using the Google Maps, you must have started the location on, then searched for a location, couple of you want to go from one place to another place. But have you think of like how does that GPS works? Any idea on that? So yeah, so what I'm asking, like when you are using the GPS through your cell phones or mobile phones, do you know how does it work? Okay, so are you sure about that it works? It uses satellites. So yeah, so that's a wrong thing. Something see, when you take mobile phones, it uses cell towers, but the principle is same. So the cell towers, it receives the signals from satellite, and then that cell towers are communicating through our mobile phones, and from that we are getting our signal data sets. So unless and until you have specific GPS sensor inbuilt in your phone, you cannot get the data from satellite, and for that we have handheld satellite. But the principle which we use in mobile phones also, this is same as GPS. So we take just cell towers or mobile towers in our locality. Let's say three towers are there. So it will give the same principle that it will do the trilateration and it will find out the our location. So principle is same, but instead of satellite, it uses the cell towers. And when there is no network from cell tower, in those conditions, it will use satellites. Why so? Because if we constantly start getting the signals from satellites, it will become very drainage, like it will drain your batteries because you are constantly operating through satellite. And because of that, it is not recommended to get like locations from satellite because it needs a lot of computation. And because of that, to like make your phones faster, we use the navigation through cell towers rather than satellite. Unless and until we don't have proper coverage of cell towers, then in that case only it will go and search for the satellite in those cases only. So initial location findings will go through the cell towers. Yeah. So anyway, if you have handled satellites, sorry, GPS sensors, or in your mobile phones also, if you have chip of GPS receiver, or if you have worked with anyone before, then it uses the satellite constellation to find your positioning. So why do we need to find our location? So why we are interested in location? Exactly. So we just want to know where we are, where do we want to go, how much time it will take, how far it is it from us. If we have some deliveries, we want to track it down, how much time it will take to reach to us, like we do in Amazon, Flipkarts and all. But that is our notification based, not the location based. Similarly, when we use Uber, Ola or somewhere, it will show our actual real-time position where we are going. And if we can, for security reasons, we can share that location information with our others, our friends, our parents, and so on and so forth. So all those are applications of satellite navigations, or in nutshell, navigation, where you need a location information of a user. So the first term when you heard about any navigation system, the thing comes first to our mind is GPS. But the GPS is very name of the constellation which is provided by USA, not the all the satellite comes under the GPS. It's like Maggie. Like if you take any noodles, you will term it as a Maggie. Or if you take like any biscuit, you will just refer it as a just biscuit, a normal name, not the specific name. Similarly, when we talk about navigation, just first thing comes to us is GPS. But in general, the full name is Global Navigational Satellite System. So it's a global systems used for navigation, and it's constellation of satellite, and it's a constellation, so it's known as a system. Now, few systems are global, which is such as GPS, which is by USA, GLONASS, then Galileo. So GLONASS is from Russia, Galileo is from Europe, Compass and BeiDou is from China. So these are the location-based satellite navigation system, which gives the coverage of entire world. And then it comes to the some region-specific satellite system, such as our Indian system, which is known as a NAVIC, or navigation with Indian constellation, or you can say it as an Indian regional navigation satellite system. And there is the QZSS, which is quasi-zenith satellite system, which is built by the Japan. After that, there are some S-bars, so it's a augmentation system, which will give us the corrections to provide the precise positioning to the users. So Gagan is our Indian system. Then VAS is also a satellite-based augmentation system, which is a wide area satellite system. And then there is IGNOS, that is another augmentation system. So basically the use of this augmentation system is to give you the precise positioning, which can be used for like navigation within the air or within the land. And on this right hand side, you can see like how, like at any given location, how many satellites are available at a given time. So the number of satellites which are present, which will change and give us the accurate positioning. So after that, these are the couple of systems. So when you learn about GPS, it's basically advisable you go through this, what kind of various satellite systems are available throughout the world. So as I discussed, GPS, it's also known as a NowStar, which is from USA and like started in 1987. Then GLONASS is from Russia, BeiDou is from China, and Galileo is from Europe. And all of these four are giving global coverage. And then there is a NAVIC, which is Indian, which is a navigational system. And once you start searching for those missions, you will also get to know that which kind of frequency they are using, at which frequency they are communicating the information with us, at which altitude it is, and then it's a operational status and how many number of satellites are present. So can anyone tell me, like in the class you might heard of, like how many minimum number of satellites are required for if you want to do a global navigation? So I'm talking about global navigation, not the users. Okay, so there is a NowStar system in which sir is talking about that you need at least 24 number of satellites if you want to provide a global coverage throughout the day. So if you just read about the NowStar satellite in the lectures, you will heard that at least we need 24 number of satellites to provide the global coverage. And that's why you can see like this GPS, which is provided by USA, it is having 32 satellites. So more than 24. Why more than 24? Because let's say if some satellite or one or other satellite stop working, then it can use the information from other satellites. And you can see like all the satellites which are global in nature, they are having at least 24 or more than 24 satellites in orbit. Whereas the India, we just have 7 satellites, and that's why it gives the regional coverage only, not the global coverage. Now, there is a two type of service this GPS is providing us. The two words you might also have heard during the lectures, which is the standard positioning service and restricted positioning service. So standard is like open for civilian and restricted is for military use. And it depends, like in standard you will get less accuracy, but in restricted service it's for military use, so you will get very high accuracy at centimeter and decimeter levels as well. And if we take our Indian satellite, so it is having this kind of 7 satellites in orbit, out of which 4 are geostationary, sorry, 3 are geostationary and 4 are geosynchronous. And this is the initial coverage. So India and around that, like in some 1000-kilometer area, we have coverage. And then this is the separate coverage where we do not get proper signals, but at least we get some data. Now, when we talk about GPS, it's a system. So system should consist of different segments. So GPS consists of three segments: space segment, control segment, and user segment. And you have gone through those things in a lecture, so we will not go into detail. So basically, space segment, I will just talk about the Indian navigation system. So you will just get some overview of it, because in lectures we have not covered these things for NAVIC or IRNSS. So India has launched nine satellites for this navigational purpose. Out of that, two are not working, so we can consider seven satellites only. And in the previous lab, we discussed about geostationary and geosynchronous satellite. So you can see now, I already talked that four satellites are geosynchronous and three are geostationary. So you can see like geosynchronous satellites are not just like on equator. It has some inclination with equator. Okay. Yeah. So after that, this is the how the satellite moves. So you can see this geosynchronous satellites are moving, whereas geostationary satellites are more or less like at similar locations only. So you can also do, if you want to see this kind of stuff, that how the satellites are moving just for India or USA, then you can go to this Trimble GNS Planning Center site. So you guys, I will just copy paste this link there. If we have time at the end of this lecture, then we will go through it. Otherwise, you can just go through this video once, and you can open this sites again, and you can just learn that how the satellite moves, and at any given point how many satellites are available in your area. Okay, so then the control segments, it just controls all the operations with the satellites and the ground communications, and it two-way communicates with the satellites and the users. Then we have user segment. It's nothing but we have just handled receivers, GPS receivers installed in our mobile phones or our GPS receivers, and using that we are just getting the data and using the data for navigational purpose. So there are single frequency receivers and double frequency. Single frequency we are just receiving L1 data only. Dual means we are receiving L1 plus some other data. Suppose S band also or L2 band also, like that. So these are the various applications of GPS, which you will see in the further lecture of next week, first lecture. But it can use for any particular task which is under the sky, but not in the underground. Like you cannot do survey under the bridge, you cannot do survey inside the tunnel or subsurface surveys. It's just any part under the sky and on land, not below the land. Then these are some high precision applications of GPS, that monitoring the deformation in bridges or on dams, then navigation within the sea, how we are sailing through oceans, and then in photogrammetry also, when we are taking images, we just want to like locate where we have took the photo. So for that also, this is important. Then, so that was the part of most of the thing in the first video. Then we have the concept of positioning. So basically, how do we calculate distance using these satellites if we have receiver? So there is a two kind of thing which it uses. So there is, what's the observables. So whatever data which we get from satellite to receiver, it is known as a observable. And then that observables are, there are two kind of observable. One is phase pseudo range, and then second one is chord pseudo range. And the word pseudo range means the distance between 2 points, and pseudo means false distance. So why there is a distance is false? Because there are lots of things coming within the atmosphere. When these rays are passing through the atmosphere, it is having interaction with a lot of things, and because of that, whatever distance we will get, that is not actual distance, but it has some error into it, and that's why we termed it as a pseudo range. And here you can see there are two kind of observable, phase and chord. So in phase, what will we do? That the rays is coming like this, radiations or signals are coming like this. we will calculate how many frequency of radiation or signal came. So let's say if it is 50 frequency, then we will multiply by 50 into the wavelength of that particular signal. So we will get the how much distance it has covered. So that is known as a code pseudo range. Sorry, phase pseudo range, where we just know the wavelength of the signal which we are transmitting, and then how much number of cycle it has covered. So that is known as a phase pseudo range, where we are considering the wavelength. If let's say if the wavelength is 5 and 5.1 half signal, then the phase will become like 50%, or like we can say phase defined by like 180. So if we take in terms of 0 to 360. And then there is another way to do the same thing, which is known as a code pseudo range. So in code pseudo range, what we will do, we will just measure the time, how much time it is taking to reach from satellite to receiver. And we find the delta t and we multiply the delta t with the velocity of light. So we will get the distance. So these are the two way how we calculate the some basic principles how we calculate. So there are two type of observable, phase pseudo range and code pseudo range. Now you might have heard about this thing. So uh, Shivam, you told about that we need just three satellites, okay, if we want to get the position. Yes. No, no. So that was the just tricky part here. So just see, when we talk about location, what are the parameters which we need? We need X, Y, Z. That is the three locational parameter. What is our latitude, longitude, and height? So if we just have three satellites, then what will happen? We know the distance, like we know the like if you see the videos, then you might have heard that during this GPS survey, the location of satellite is known to us, but this location of this reserve this point where we kept the GPS, it is not known to us. So we want to find out this point X, Y, Z, and T. So what we will do, we will find the distance between this point and this point, which will become x1 minus x square plus y1 minus y square plus z1 minus z square is equal to r square. Because we know that how much time the signal is taking from reaching from satellite to receiver. So we know that delta t and we multiply with the speed of light. So we'll get this equation, which is just distance equation. So this is the first equation. Using the second satellite, we'll get the second equation, and third satellite, we will get the third equation. So if we have three unknowns and three equations, we can solve the problem. And okay, but the problem is when the satellite is transmitting the signal, they are having very high resolution clocks, which is made up of cesium. Because of that, there is a satellite clock error. And because of that, when this signal is reaching to the receiver, it has some time delay. And that's why to avoid that time delay, we also measure the time at which it is reaching to us. And because of that, we need at least four satellites because to avoid the error coming due to time. Okay, so that's why we need four satellites. So if using three satellites, we will not get the proper answer. So if you attempt any questions that how many satellites are required, so the proper like in GATE or anywhere, like these questions were also asked in GATE examinations, in geomatics as well as in civil engineering. So number of satellites required for GPS positioning is four only, not the three. And the way how we calculate this process is known as an analytical resection. So analytical resection is we know the distance between 2 points, and using that distance we are finding the location of unknown coordinates. Okay, any doubt in this? The basic principle of positioning. Yes, for time factor. Okay, so what will happen? Yeah, yeah. So basically we want to find a location. Okay, so for that we need three parameter x, y, and z. Okay. Is that clear first? Okay, now what will happen in GPS survey? We will be having this thing. Just give me a second. Put my pen on. So basically, we know the like when satellite sends data to receiver, it knows what is the location of satellite and how much time it is taking to reach from here satellite to positioning. The time we also know. So if we know the time, then we can use this formula that how much time it took delta t and multiply with the speed of light. So we will get the distance between satellite and receiver. So that distance is d1. How we will get that? Multiplying the delta t into speed of light. For this satellite number 2, the distance will be d2. Here it will be d3 and here it's d4. Okay. Now if we know the distance, we can apply the distance formula. What is the distance formula is, let's say if we have d1, then the distance between 2 points is given by, like we do in Cartesian distance. So under root of x1 minus x square. So under root of x1 minus x square. Similarly y1 minus y square and z1 minus z square. Did you get my point? Okay, so if we have this equation, we have written for satellite number 1. Now same equation we can write for satellite number 2 and satellite number 3. So now we have 3 equations and 3 unknowns which we want to solve: x, y and z. Okay, so 3 unknowns we have. So 3 equation, 3 unknown, we can solve the systems and we will get the answer. Is that fine? So that is a theoretical point of view, how we get the position. But now, why there is a need of fourth satellite? So the thing is, when this satellite is transmitting the data, at that time, the clocks which are mounted in this satellite, because what we are doing is, we are finding that C1, D1 is equal to C into delta T. Okay, so if there is an issue with delta T, then it will create issue in this solving these equations also. So to make sure the time which we are getting is accurate, here we use cesium clocks which are having the like precision of 10 to the power minus 12 seconds. But the clocks which we are having at receiver side, they are having the precision of 10 to the power minus 3 or 10 to the power minus 4 seconds only. So there is a very big difference in the precision of the clocks which we have in satellite and receiver. And because of that, there is a delay in time and time will also become uncertain. So we need another parameter to solve this satellite clock error. And that's why we need at least 4 satellites because of that reason, to avoid satellite clock error. And if you have heard in the error budget, the error which is coming through the satellite clock, it's largest, which is around 5 to 7 meters. Okay, so just because of that, we need another parameter which is a time, and that in formula we will write it as C delta T. So this equation plus C delta T. So delta T is a error in time. So error in time for satellite 1, error in time for satellite 2, error in time for satellite 3 and 4. So now we have 4 unknowns: x, y, z and delta t. So we will have 4 equations and 4 unknowns, and we will solve this location of x, y, z and t. Did you got my point? Okay. So if you appear for any exams, or if you just look into GATE examination previous year papers also, you will find the answer as a 4. But others like courses also. So there is one more course on GPS surveying in NPTEL. So you can go Like if you are interested, you can go through that course and read more about GPS from there. Okay, so this is the equation which I'm talking about. So this equation plus there is a issue which is coming because of the clock at the satellite and receiver end. So this is like how we can define this in terms of mathematical way, what we are getting directly as coordinates. And like this is the like once we get this kind of equations for all the four satellites, then obviously we have to solve those equations, and that is like purely mathematical part. So to do that, we just use lots of Taylor series expansions, and then after we use differentiation and this kind of stuff, and we will end up with some answer of x, y, and z. So right now we will not go into these things that how we derive these mathematical calculations. But if you are interested, you can go through the books. So this is the solution how we will achieve, and we will come back to these solutions again. So once you solve all the equations, you will get something like this, and this delta x is the your coordinates. So this delta x can be found out by solving this particular matrix. B transpose B minus 1 into B transpose delta rho, whereas rho is a pseudo range observables which we are getting like change. And have you heard about this term like geometric dilution of precision or DOP value dilution of precision into your lectures? So there are four terms in the last lecture. If you see when you are talking about sir is talking about different errors. There, yeah, okay. So there is a so there is a satellite geometry. How we can keep this satellite geometry so we'll get the precise positioning. So those GDOP, PDOP, all those came from these equations only. So I will show you the actual how the formulation, how we can get the formulas for that as well. So now when you take any GPS data, it will look something like this. So it's kind of signals. So first thing is a carrier wave, which will carry the signal of satellite which is coming. Then there is a spreading code, which will spread the data so that it will not get mixed through this cheap rates. And like which is CE code and PY code and all those things. This is your carrier waves is your L1 and L2. If you have heard of this L1, this is the wavelength corresponding to L1 signal. And this is similar to C code and PY code. And then there is a navigational data. So all the details about the satellite X, Y, nearby satellite, all those things will be kept by like collected using this navigational data. And at the end, what we get our end is composite signal, which looks like this. So when we receive the signal, it is looking something like this. Now, this carrier waves, it will just carry the signals which we are getting through GPS satellites. And there are L1 code, L2 code, L5 code. So these are the different kinds of carrier waves. And you can note down the frequency. L1 is having highest frequency, L2 is lesser than that, and then L5 is a new range. So if we use L5, we can do a lot of other thing, penetrate through to like different things, canopy, and sometime under the tree or under the bridge also we can penetrate if we are using this L5. So this signals can pass through clouds, glass, vegetation, plastic, but cannot pass through the solid objects such as building and mountain. So if you are within the building, you will not able to get the things, your signals or your locations most of the time. That's in basement or such kind of thing. Now, what does this carrier waves will carry is pseudo random number. So pseudo random number is when we are getting some codes from the satellite. So it's a unique identification number which we are getting. Using that, we will use that code pseudo range or the phase pseudo range observations, and we'll find out the distance between satellite and receiver. Then there is ephemeris data, which is about satellite. What is the location of satellite, whether it's healthy or unhealthy, what is the date and time actually in satellite. So to track down the error which is coming because of time, and all those data will get as ephemeris data. And there is also one term which you will heard, which is known as the almanac data. So almanac data is so So almanac data is the data about the nearby satellites or nearby stars. So what it is showing. Then there is a ranging code which will range our signals. So it will combine with the carrier waves and it will give us the data. So this this carries our this PRN code is inbuilt in this ranging code, and first it will be L1 and L2, and then after this will come, which is your CA code or PY code or L2CM code or L2CL code. So all those will come after. So first is the carrier wave, which will be L1, L2 or S, something like that. Then ranging code will come, which is a CA code or P or PY code or L2CM or L2CM code, such as. And then comes to the navigational method. So this is kind of like how the pseudo random noise or the PRN number looks like. So what we do, we get that number from satellite, and that same number we generate within the receiver also, and we will try to match at which time it is matching. So if the signal, like in receiver, we have the database of all the satellites, and every satellite has its own PRN number. So once it matches with the different library of PRN which is available in the receiver, it will find the cross correlation and it will find it is matching with which particular signal. And then after, once we find that it is matching with which signal, then we will take both the signals and we will find how much time delay is there, delta t. So once we get the delta t, we will multiply with the speed of light and we will get the distance. So basically just matching with the PRN values and getting the proper signal and then finding the delta t. And this is like more information about P code and CA code which we use in GPS. Any questions? Okay. So you just keep in mind about the at what wavelength it operates and at like what frequency it has. So it will help you to identify like how it will affect the signals and errors. So then after we have different terms which you should know, such as integer ambiguity, cycle sleep, selective availability. So selective availability is like earlier these signals were used for defense purpose only. So it will introduce error into the signal. So after 2000, they have removed this selective availability, and after removing that, we are getting little bit high accuracy. Earlier, earlier if you see, because of this selective availability, around 30 or 30 plus error was coming, but after removal of it, it just became zero. So if you see the overall error budget, which is of GPS, then earlier it should be around 33.3 some kind of errors if you combine everything, positive, negative errors, and which reduced to 8 meter nowadays. So this selective availability is just introduced by the government to just like make some noise with your signal so that you cannot get the actual positioning. But they removed this after 2000. So basically the key point if you are appearing for any exams which you have to mind or like keep in mind from these signals is L1 CA code has lowest ionospheric errors, which is like which we'll talk about what ionospheric error was in the error sections. This L2C has the best cause correlation performance, and L5 is the newest generation of carrier waves, which has highest power and it can like penetrate to different stuff which L1 and L2 can't. So each signals have their unique strength, and according to that we use that which signal we should use. Now coming back to the error part. So if the you are getting the data from satellites to the receiver, first of all, like if we say it will has to come through the atmosphere and it has lots of error, which can be a gross error, systematic error, or random error. So gross error, it can be any error which is coming from the human interference or we are not doing a proper survey. Systematic error is error which we can model and mathematical in nature. Whereas random error, it's just coming just because of some reason or something happened during while doing the survey. So this error we can divide into three components. First is error which is coming due to the atmosphere or space fragment. So in space, what is there? We have satellite and we have one orbit in which it is moving. So we can have error due to satellite orbit and error due to satellite clock. Then after, once the ray is coming through the atmosphere, it will interfere with the ionosphere, and then when it comes near to the atmosphere and Earth, it will interact with the gases present in the atmosphere, which will cause the tropospheric error. So here ionospheric error will happen, and then after tropospheric error will happen, and then after, once the signal will reach to the receiver noise error will happen. Then we have errors which is coming because of the receiver side. So receiver side, what can happen? The antenna is not proper, so we'll get the multipath errors or antenna phase center errors or receiver clock error. So this is like how the error propagates from space segments to the ground segments and the location where it get errors. So do you guys want to know more about errors? Then we can discuss this. Otherwise, we can skip and go to the question answer part. Okay, so if time permits, then we'll talk more about these errors. Yes, yes, you can. You can go through the videos afterward. That's fine. Okay, that's no issues from my side. You can join. Okay, so let's get started with the questions of GPS. So the first question is which of the following can indicate the correct set of GPS segments? So control and user, and there is no something like as navigational part. So because of that, the option A, B, and D are wrong, and C is correct. Just, we'll make it. So C is the right answer. Now, the fully operational GPS constellation comprise of how many satellites? Okay, so the answer is 24, as we discussed in the beginning of this class. The next question is L1 band in GPS receiver has a frequency of, yes, so L1 is having around 1500, L2 is having 1200 around, and then this P bands or P signal, it is having 10.23 megahertz. Then you have two type of positioning, standard positioning service and restricted positioning service. So which of the following is true for standard positioning service? So this is a standard one. So there is two, standard and restricted. So from name or name only you can just think of that standard is for civilian use, not for military. Okay. So one option is SPS is for military, sorry, it's for civilian purpose, not the military purpose. And any one from this is correct? Uh, no, actually it has 100-meter horizontal accuracy. If you take your answers were right, but if it is given as a restricted positioning system, not the standard, or you can say precise positioning system. Okay. So in that case, this answer is right, option B and C. But if it is given as a standard positioning system, then it has very less horizontal and vertical accuracy, and it is designed for civilian use only. So option A and D is correct. What does the pseudo-random code help the GPS receiver to measure? So what do we measure through signals which we are getting from GPS? No, so what it is giving that we will do at the end. So here, what I talked about is, I talked about two methods, that pseudo random number or the code which we are receiving through these signals. So that will help us to determine what? Exactly. So it will help us to find out the travel time. Navigational data will help us to find out the satellite position. And signal frequency is just like it's just constant. A number of satellite will determine your geometry and then further the accuracy of your systems. So the answer is signal travel time, delta t. By comparing with the different signals and finding out the delta t, multiplying with the c, you will get the distance. Next question is satellite-based Navstar GPS augmentation systems are. So as we discussed in this class in the first slide only, yeah, so that is from USA and other two are also part of augmentation system which are Gagan and Ignos. So those two are also wide area. Yeah, so this VAS is stand for, that is the next question. Yes, so option C, wide area augmentation system. If any one of you feels that you don't know the answer or if you need an explanation of it, please let me know because this thing you have already done and these are the theoretical questions only. So I expect you to answer. If you do not know or if you need explanation, please just let me know. So we'll discuss the each and every options also in that case. So this VAS is a network of, right? Exactly. So it's a combination of ground stations and geostationary satellite, which will measure the accurate locations, finding out the bias, and then that bias or error it will augment with the other system so that it can improve the positional accuracy. The next thing is the component of GPS signal that get received by all types of GPS receivers. So here the answer is CE code, which is very general in nature and it can be found with any signal L1 or L2 or L5. Yes. So this is just a theoretical question only. So we have first carrier waves, which is L1, L2, L5. Then the GPS signal, which is carried with this carrier waves. So it can be a CA code, it can be a PY code or L2C code or L2CM code. So it is like you just have to go through it. So this CA code, it is available for L1 also, L2 also, and it can be accessible through all the receivers. Okay, so you just have to remember this thing and the combination of it. So you have to see various satellites and you just check the combination. Now the next thing is for 3D positioning requires how like this satellite based navigation system requires minimum of how many number of satellites. So the basic objective of GPS is to provide service for. Yes, so velocity we will not get. Why? Because it is a derived product. Once we get the position and timing, how much time, like how we are changing our location with respect to that time, and then after we can find out the velocity. So velocity is the derived parameter, not the initial parameter which we get. Then we have which of the following is not an output of a space segment. Yes, so it is the output of user segment where we receive the final coordinate. It will not get directly from space. Which of the following gets mitigated in DGPS positioning? No. So what is DGPS first? Okay, no. So what is DGPS first? If you understand the concept, then it is easy to differential global positioning system. So what we do in DGPS, next thing, rover. So we have GPS, two stations, base station and rover stations. Yes. So what we do is we first of all we know the coordinates as base station, and then after we get the same data for the same station where we know the actual coordinates. So we find out the error in delta x, delta y, and delta z, and that error we will correct in every other observation. So now we are correcting in other observations. So when we can correct if the error is same for both the can you stop your mic? Atul, can you mute your mic? Okay. So basically, yeah. So if the error is common for base station and rovers, no, no, no. So what I'm telling is, if error is same in the rover station and base station, then it can get removed from DGPS. Okay. So now which error is common for both? So what I'm saying is, see, I will explain through figures so you will get more idea about it. So what is there that let's say this is the satellite and this is the receiver. Okay. Now let's say receiver is here. This is our base station and I will put another receiver which will work as a rover station. So which error is going to be remain same for both the case? So this satellite error will be same for both. If it is coming from said satellite, then satellite clock error will also same for both. Now ionosphere, so it is coming from the same environment. So ionospheric error is also same for this station and the station which is nearby. Tropospheric error, it is also part of atmosphere, so that will be also same. Receiver noise, so noise which is coming in the atmosphere, that will also be same. But when you reach near to the surface, what will happen that such as I will just show you. So now you can see in this figure, you can see the base station and rover station. Okay. Now here what will happen that here if lights or radiation signal is coming at base station, then it might interfere with this part and then after it will receive over here. And for this rover station, what will happen? It will go to this building and then it will come to this. Okay, so this is multipath error. So multipath error can be different for both. It is not same for reference and rover. So that error will be different for both, and that's why multipath we cannot remove using DGPS. Similarly, error which is coming from the receiver clock. So one clock is there in rover, one clock is there in this base station. So both are having different errors. So that's why receiver clock error also we cannot resolve using the DGPS. But if you see the atmosphere, so atmosphere is same. The area of atmosphere from where the signals are coming, it is same for both rover and reference. So we find the same thing for this reference and that we will correct it for rover. So whatever is in atmosphere, which is your satellite clock error or your satellite orbit error or some other error which is coming due to the atmosphere, which is ionosphere, troposphere, that will be same for both base and rover. So whatever error is common that we can remove using DGPS. So here the answer is atmospheric errors, which can be mitigated using the DGPS. Not the multipath, not the cycle sleep, not the topography. Topography is also like nearby area, like uh, near to base station you may have hill and near to rover station you do not have anything plain. So near base you will get more error, where near rover you will get less error. So topography is different for different location because these are the parameters which are changing near surface. Similarly, cycle slit is something coming in obstruction to signal. So let's say some bird came or some tree came with rover, and because of that rover is didn't get the proper cycles and it just got the slip. And once again we got the signal back. So that condition will be different for rover and base station. And because of that, that is also different for both. So whatever error is same for both that we can remove using DGP. So differential is like here when we take any data set from satellite, we can write the signal like distance between satellite and base station D1 is equal to the C into delta T, C into delta T. I will just write this as a delta T. So this is our actual distance. Now we have satellite clock error, let's say CT, plus we have atmospheric error AE, plus we have surface error, which is because of the receiver error. Now similarly we will write for D2. So D2 also we will write C delta T. So this might be different. Okay. Yes. So this one is common. So when we take the difference, when we do the D1 minus D2, whichever is common, that will get removed. Okay. So just keep attention because these questions are very tricky in most of the cases. Yeah. Next. Yes. 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 Okay. Yes. Hmm. Yes. Yeah, so basically when we do the GGPA survey, so there is a need that we need at one location we need to get the data. Then and then we can find out the error and that error we can like correct for all the nearby stations. But let's say in area where you do not have any reference point, so in that case what we will do that we will take long reading at the one location only. So we will take for longer time. Yes, so for base station, we'll take a longer time reading and we will consider whatever we are getting at the base station, it is correct. Now we will same take same reading for one more time and we'll find out the error. So at base station, two readings. Yes, yes. So anyway, the main point or principle of DGPs is that only that you have one particular point which is where which location is known to you. If in your area if it is not known, first you will get the data of that station. So in that way when you are doing survey where points are not available, so it is relative to the one point which you are fixing. Okay, in that case also it will remove the satellite error, atmospheric error, but it is with reference to base station. Yes. uh, Basically what I mean. Okay. Yes, URS networks. Yes. 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 So yes, yes. CORS is also part of DGPS only because we will fix a CORS station at a particular location. So where we know the location. And then after, like, that's why this government of India, Survey of India, just started this making various CORS stations. So they find the whatever where we have CORS stations, we will know the locations using long-term monitoring at the same location, and we found out the error what we have in. So that error we are transmitting with the nearby station. So if I'm going to start my survey in the nearby area, first I will acquire the information from CORS network. I will connect my DGPS, or sorry, GPS with that, and then it will give me the answer about the errors. And that error I will add into the different points while collecting the survey points. Yes, so yeah, so there are already lots of stations came up in Gujarat. Also, some stations are there for CORS network, and few surveyors are already using it. And like few years back, Survey of India just had launched this project where they are like more than 200 or 300 CORS stations they are about to build in some of the areas. So that was I just checked on. It's a it's a NAVIC. Gagan is augmentation system for like in the space segment. We are getting CORS station, we are using NAVIC as well as other system also. It's a combination of multiple satellites. Yes. See, basically, NAVIC is indigenous system, which is regional specific, whereas GPS is global system. Okay. If you want to see that, if you want to relate both of it, what you can do is you go to any point where you know the actual location and you measure the same thing with NAVIC and same thing with GPS. And how much error you are getting, you just find out that equation. Or you can take multiple readings and you get the statistical relationship between this correlation or something like that. You just make a formula out of it and then you apply. So there is no current formula, but what we do in practice is if you want to get from one to another, we collect the data using both and we establish the statistical relationship between those two. Yeah. So yeah. So now we'll I think go to next question. So next question is Nowstar GPS consists of minimum of 24 satellites. Then the second is precision of GPS positioning is being defined by its standard deviation. The third is DGPS method provides more accurate 3D position than relative static post-processing method. And fourth one is GPS observation from geodetic GPS receiver provide less accurate position than GPS code receivers. So which of the following statement is correct? Yeah. So if let's try to get track it down. So the first option is it requires minimum 24 satellites. So that is true. So option A is correct there. The next one is this precision of GPS positioning is being defined by its standard deviation. So when we measure the error of GPS, we see there's a location uncertainty is in plus or minus standard deviation what we have. So that's why the second is also true. Now the third one, DGPS method provides more accurate 3D position than relative static post-processing method. So here they are using the word post-processing. So post-processing is like once you come to lab, you find out the error in one of the known point and then using that you are correcting the error in the different parts. So that also after doing the survey, whereas DGPS will imply that on field. So we will get more accuracy while doing this relative static rather than DGPS. So the option C is wrong in that way because of just post processing part. Then the next thing is GPS observation from geodetic GPS receiver provides less accurate position than GPS code receiver. So geodetic is like more advanced one and it is providing more accurate rather than code receivers. So that is just a normal statement and that's why it's wrong because geodetic is more accurate than code receivers. Code has lots of error because of ambiguity in other parts. So option A and B are correct. The next one is identify the correct statements. So for accurate positioning, geometric dilution of precision, also known as a GDOP, should be as large as possible. So here the value of GDOP or dilution of precision should be minimum by doing the GPS survey because it is a measure of satellite geometry. So if our satellites are spread well, then we get a very good signal and we'll get more good positioning. If all the satellites are like concentrated over one part of this receiver, then we will the uncertainty band will increase, and because of that it will create a error in the positioning. So here, if for proper survey, the value should be as minimum as possible, not as maximum as possible or as large. It should be as smaller as possible. So that's why option A is wrong. Second option is integer ambiguity is associated with carrier frequency observations of GPS. So integer ambiguity, as you can just heard about from the name, that is coming when we are measuring the observable as a carrier waves. So when we are measuring the carrier waves, we will calculate how many number of cycles of wavelength passed. So what is the frequency of it? And then we multiply that number with the wavelength. So we'll get the distance. But if we have some issue in counting that numbers or if we miss something, then it will create a error in the observable, which is known as a integer ambiguity. And it is related with the carrier frequency part. So this statement is correct. So I will show you in depth about that integer ambiguity part as well. So basically, when we have this cycles, so if we are not able to measure the actual number of cycles, then this integer ambiguity will come into picture. GPS is one-way ranging system for users. So that is like as a user, we can just get the data from GPS receiver, GPS satellites. We cannot give data to the satellite. So because of that, when we are using GPS, it's a one-way ranging system, not the two-way ranging system. But when we talk about control part, like or when we talk about control stations, so the thing is, next thing is when we talk about the control station, then it can communicate both with the satellite also, and like we can get data from satellite at control station also, and we can also give our data to satellites. Why there is a need to give data from control station to satellite? Because let's say the orientation of satellite moved a little bit, so to make it well, whether if it is not healthy, then what to do. So those codes will get in our ephemeric and almanac data, and using that we'll also make it calibrations and validations in the satellite from control stations. So if it is for control stations, it is a two-way ranging system, but if it is for user, then it is a one-way ranging system only. Then we have the next question: which segment of GPS system includes GPS receiver to obtain positioning information? So here, the answer is user segment because as a user, we are collecting the data of XYZ point. The next thing is during GPS survey, initialization of rover receiver is required for which kind of method? So here, if we do any kind of kinematic method, which is like relative kinematic and stop and go, during that time, we need to fix our rover and we have to do the initialization of it. Whereas in static method and kinematic go and fly method, we do not need separate rover receiver, which we have to initialize. Then the next one is GNSS, which is Global Navigational Satellite System, stands for this Global Navigation Satellite System. So as of today, which of the following is complete set of GNSS constellation, which gives the coverage over entire globe for all the parts of world? So which of the constellation gives global coverage? So already we know that GPS is from USA, which gives the global coverage. GLONASS is from Russia, which also gives the global coverage. Galileo is from Europe, which also gives global coverage. Baidu is from China, that also gives the global coverage. IRNSS is from India, which gives the regional coverage. QZLSS is the again regional system from Japan. Whereas if you see Gagan, VAS, and IGNOS, those are not the navigational satellite system, but although they are augmentation systems. So that are not a part of navigational satellite system, that is a part of augmentation systems. So our answer will be GPS, GLONASS, Galileo, and Baidu. The next is space segments get interfaced to user segment through which band. So as we just discussed in the few questions up, that space segment and user segment is just one-way ranging. We can just do the communication, we can just get the data from satellite. We cannot send data to the satellite as a user. So first thing is it's a one-way ranging and it is using L band to do that. So L1 band, L2 band, that's the thing. If we are using control stations, then if the answer is space segments get interfaced to control segment through, so then the answer will be two-way ranging system with the S band. Now the next question is, in case of GPS positioning, position of which part are considered as to be known position? So here we discussed in the theory part that yes, so satellites, we know actual location of satellite, which is coming in the navigational data or it's ephemeris data, and using the equations from satellite and receiver, we calculate the x, y, z, t at the reference point or the control point or user point. The next question is, the basic premise for using DGPS technique is to reduce the error due to. So can anyone give the answer? So what we discussed till now is, if the error is same for rover and base station, we can remove it using DGPS. Yes, so atmospheric error, satellite orbit error, but multipath error, it might not be true. Why? Because let's say we kept base station and there was so many buildings or so many trees near base stations. But near rover, where we are moving away from this station, there is less building or less trees or very plain area. Or let's say we take the another situation. We fixed our base station in the plain area, and when we are moving into the nearby area through rover, we got some buildings or we got some trees. So multipath error, it's a nearby object. So it might be different for base station and rover station. So atmospheric and satellite orbit is right, but multipath is not correct. Similarly, if we take the option B, so atmospheric and satellite, yes, no, receiver, see, receiver we will have in both. Base station also we will have receiver and rover also we have receiver. So both receivers are different. So they have different errors. So receiver is also not true. The answer is satellite clock, because satellite from which we are getting the data is same for the base, same for the rover. Because of that, it is common in nature and we can remove the error because of satellite clock. So whatever the parameters are there in space segment, that we can resolve, and whatever is there in atmospheric errors such as ionospheric error, tropospheric error, and receiver noise errors, which is coming due to the atmosphere, that we can remove. But we cannot remove multipath error, receiver clock error using DGPS. Is there any doubt in that question? Okay. So the next is the orbit period of GPS satellite is determined by which of the orbit. So which parameter of orbit helps us to determine the orbit period, how much time it will take in going through the orbit. So as per the Keplerian parameter, the semi-major axis will define the orbital period of satellites. So how much time it will take to finish one round or entire part. So that will be determined using this semi-major axis, not using eccentricity, not using inclination. The next question is, which of the following methods is widely used by GNSS constellations to distinguish the satellite from each other? That this is the Indian satellite, this is the some US satellites, this is the Russian satellite. So for that they use CDMA technique, which is code division multiple access, and there are a couple of stations which are there in India also for our own system for this sending and bifurcating the signals. So that is known as a code division multiple access. The next question is, which of the following statements concerning GNSS error is or are correct? So the first is tropospheric delay increases with increase in relative humidity. So tropospheric delay, which we have, it is because of the tropospheric part of the atmosphere where dry and moist gases are present. And moist is like your humidity and dry is your oxygen and nitrogen. So that will create the atmospheric delay. So if we increase the humidity, it will slow down the signal which is coming to us and it will make a delay. So delta T will be high. So tropospheric delay increases with the increasing relative humidity. It means if more humidity, more time it will take to reach, and because of that, more delay it will happen. Next is ionospheric error is highly correlated with the position of moon. So that statement is wrong because ionospheric error is because of the ions present in the ionosphere, which is highly determined by the sun's energy, not the moon's energy, or sun's radiation, not the moon's radiation. So option B is incorrect. Next question, next option is multipath error is caused by buildings and man-made features and not by the vegetation. So is it true or false? True. So okay, why, if there is a big tree, will it cause the multipath error or not? So if you are doing a survey in jungle, there are lots of tree and this, let's say, a dense forest is there. So it will create a problem obviously because it will obstruct the signals. And because of that, we can say that multipath error is not just, it is because of the environment, what object we have in the environment, whether it's natural or man-made. So it is because of building, it is because of the man-made features, and it is also because of the vegetation as well. So option C is false. D, the observed range is called as a pseudo range because of its erroneous nature. So is it true or false? So this statement is true. Why true? Because observed range, what we are using, code pseudo range and phase pseudo range. When we are measuring this delta T, we have error coming through the different components of the space, atmosphere and receiver side. Because of that, it will not give us the actual distance and it will give the distance with some error. So because of this erroneous nature, this word pseudo is there. The meaning of this pseudo word is false measurement. And this false is because of the error of the different components. So that's why option D is correct. So option A and D are correct, B and C are incorrect. Any doubt in the explanation of 20, like question number 24? Yes. Hmm. So if any object is very big, so like you have to think about like how this scattering used to happen in the previous class we discussed. Relay scattering, Mie scattering, and like that. So if the signal which we are receiving, which is your L1 and L2 signal or L5 signals, so the wavelength of it and how that wavelength is interacting with the object. If it can bypass the object, it will not create the multipath error. But if the wavelength is big and if it will collide with the nearby vegetation or buildings or man-made features such as tractor, or you can just take any vehicle, it will also create the error. So that's why when we fix a location of any permanent GPS point, we will find a location which is quite up in sky, basically on the, like, we take very plain area where nothing is there, or else we can fix that on a terrace where we do not get most of the time like obstruction from nearby building, trees, or any other objects. So considering, like, it will not have, like, basically it will go to another object and then it will come to receiver rather than directly coming to the receiver. So to avoid this multiple collision or reflections and then it will come to receiver, it is just multipath error. And multipath is very random in nature. It can come because of the any nearby object. So to reduce it, we cannot do much. We can just put our, like, receiver in such a location where it is do not have obstruction for nearby objects. Okay, it can also create due to the topography as well, because if we have slant in uh, like unhilly kind of topography, then it will come with the different, like, it will collide with the terrain and then it will come to receiver as well. So in that case also it will create multipath error. Yeah. So next we have numerical. A GPS satellite is flying at a distance of a 20,000 kilometer from the observer. Now the phase of L1 carrier in a degree as received by the observer is how much? Assume that the signal did not experience any refraction, reflection, or any other error, and the speed of light considered as a 3 into 10 to the power 8. So basically it's a kind of question where we want to find out the distance. So what we do in distance, we just multiply with the delta t. Uh, okay, so what we do when we calculate the distance, we multiply it with the delta t, or we multiply it with the number of cycles plus fraction of phase. So here what we will do is, first we have a formula that c is equal to f lambda. Okay, so anyone has, like, how to solve this, any idea? So C is given. So we might proceed with this formula because this is the only thing which we know, that velocity, which is 3 into 10 to the power 8, is equal to F, which is the frequency of, and this lambda is the wavelength of it. So we know this thing. Now here, what do we have? We have C, we have F. So what we can get? We can get the lambda. So we can write a equation that lambda is equal to, so yeah, so lambda is equal to C by F. C by F. Now we know what is C, which is 3 into 10 to the power 8. We know F, which is 1575.42 megahertz, which is 10 to the power 6 hertz. So we will get the lambda. Now we want to find out phase. Okay, now phase, how we will define phase? So I will just give some idea of that first. So let me take a blank screen. So let me take this blank space. Let's say we have, this is one wave. Okay. Now this is the another wave. So this is the one wavelength. This is the another wavelength. And your satellite is over here. And your receiver is somewhere here. Okay. Now to reach to the receiver, it will again go like this. And it will get the receiver over here. So now what we have how many full cycles we have? This is the first full cycle. Then this one is the second full cycle. And then we have another cycle which is just half cycle. It's not a full, but how much? It's just 50% cycle. So how we define phase is 0, 90 degree, 180 degree, 10 to 70 and 360. So here our phase will become 180. And if we want to see our phase in terms of the fraction, then we can say it is a lambda by 2. So there is a phase which we have, because see here if it is full cycle then it is a lambda, but here we have two full lambda cycle, so the distance between these two will be 2 lambda plus for the third cycle is just half lambda, so lambda by 2. So this lambda by 2 is known as a phase. Okay, is that clear? What is phase? So we want to find out this phase, how much phase we have. Is there any issue in understanding question? Okay. So now if there is no issue, what we can do is we know what is a lambda. So now what we do, we have the distance which is 20,000. So that distance we will divide with the number of wavelength, and if we get the integer number, then we do not have any phase shift. If we have some number, then we will calculate with respect to lambda that how much fraction of lambda it is, whether it's a lambda by 2 or lambda by 4. So number of cycles is equal to total distance, which is d. So n is number of cycle. So we can write n is equal to distance divided by our wavelength. Okay. Now distance we have as a, how much distance we have in the question? 20,000 kilometer. So we will write 20,000 into 10 to the power 3. Okay, we convert it into meter. And for lambda, lambda is c by f. So we will put c by f over here. So c is 3 into 10 to the power 8 into divided by f. So that will go into up. That will go up. So we will have f is 1575.42 10 to the power 6 part. Okay. Now if you solve this thing, what you will get as the answer of this is 10, 0, 1, 0, 5, 0, 2, 8, 000. So this many cycles are there between satellite and your receiver. And you can see here, this number is integer. And as it is integer, there is no phase shift. So your answer will become 0. So here there is no phase shift. So your answer is 0, or you can say, if you want to type it numerically, 0 like this. Any doubt in this question? Any doubt in this question? Okay, then we'll go to the next one. So the next question is range accuracy with microsecond accurate clock in the GNSS receiver is about 300 meter. Accuracy of GPS is 300 meter at receiver clock, because receiver we do not have much accurate timing information. It's just a 10 to the power -3 or -4 precision only. Now if we improve the clock accuracy to 3.3 into 10 to the power -x, then the range of accuracy becomes 1 centimeter. So what, find the value of x? So how we can find out the, improve the clock accuracy? So first of all, we don't know anything here. So first of all, what we will do, we have just one formula with us, which is c is equal to f lambda. But here, can we use that? Okay, we can we use that? C is equal to f lambda. Can we use that? Because here there is no part which is coming from the velocity part. Like it's not something frequency or something is given. So how we can proceed to this thing is we can just write the normal velocity formula. So what is that? So velocity v is equal to distance traveled divided by time taken. So distance by time. Now what is given to us is receiver has accuracy of 300 meter. So if the accuracy is 300 meter, V is 3 to 10 to the power 8. So we can find out the accuracy in time. So T will be D by V. Yeah, if you have work, you can go through the recordings afterward. So we have this, we can write T is equal to D by V. We'll just put V into denominator. Now we have this D and V. So we'll put the value of D and V. So D we have as 300 meter and V which we have as a 3 into 10 to the power 8. Okay. So if you solve this thing, then you will get 3 will get cancelled out and we will get 10 to the power minus 6 here. Okay, so in the first condition, if we like resolve this line number 1, then for that receiver, positional accuracy is 300 meter and time accuracy is 10 to the power minus 6 second. Now this is the like representation of first line. What is the second line? If we improve the clock accuracy to 3.3 into 10 to the power minus 6. Now here the clock accuracy is 10 to the power minus 6, or we can also write it as a 1 into 10 to the power minus 6. That we are doing as a 3.33 into 10 to the power minus 6. So let's put that value. Instead of t, what we had, we put this value of 3.33 into 10 to the power minus x. Now obviously if we put the value, then what will happen? D will change because anyway V is same, 3 into 10 to the power 8. Yes, any question? Okay. So here we know that V is same for both. So D will change if we change the time. So here in this second line, it is given that this positional accuracy will become 1 centimeter. So earlier it was 300 meter and now it became 1 centimeter. So instead of 300, we will write 1 centimeter. So 1 centimeter is equal to 1 into 10 to the power minus 2 meter. Okay. Now we have this formula. We know everything. We just don't know the x. So if we multiply 3 into 3.33, we will get the around 9.99. So we'll take it as a 10. Here also, if this will go up, so 10 to the power minus 2 into minus 8, so it will become 10 to the power minus 10. And this 10 will come, so it will become 10 to the power minus 11. So what we will get at the end of this is, so we will get something like this, 10 to the power minus 11 is equal to 10 to the power minus x. So the value of, if we solve this thing, you will get this. So the value of x is equal to 11. Okay. Any doubt in this? Okay, so our answer for this question is 11. The next question is, which of the following option best describes the uncertainty in a measurement? So basically when we talk about uncertainty, it is coming because of the systematic error and random error, not because of the gross error, because gross error can happen because of the humans, or it can be anything which can be just we can neglect through precise planning. So mostly the uncertainty when you heard it is because of the random and systematic error. The next thing is a distance was measured as 200 meter plus or minus 1.1 meter. So what is the relative precision of the measurement? So we are getting like zero point 0.1 meter error when we have 200 meter. So what about for 1? So we just take this thing. So if we just want to find this thing, we can do. So we can just write down the equation for this. So we can write down this, express this error as 0.1 divided by 200, which will become 1 divided by 2000. Okay. So in 200 meter, error is 0.1 meter. So if we take 1 meter error, then how much error it will create? So it will create error of 1 to the 2000. So option C is correct. But if I will change this question to, instead of meter, if I just write centimeter here. So in 200 meter, you are having error of plus or minus 0.1 centimeter. So first of all, you have to correct the units. You have to convert both in meters, and then after you have to solve these questions. Okay. Any question in this? Question number 28. Okay, so if there is no question, we'll move forward and solve the next question. So which of the following mathematical principle is applied for finding a geographic position on Earth's surface using GPS? So this is known as, yeah, trilateration. Yes, that is right. Which of the following is not a segment of GPS to determine position and time? So which is not a component of GPS? Yes, true. There is nothing like launch segment. Dilution of precision in GPS-based survey is primarily used to assess the quality of which parameter of satellite? Altitude, geometry, atomic clock, or velocity? So this dilution of precision is measures the satellite geometry. So what is the spread of your satellite? Basically, it measures that. So when we consider this GDOP values, it is looking something like this. So if your satellites are distributed away from each other, then you will get some, while you do the intersection of all four, you will get one location. But if it is nearby, as you can see in the this side, or like all satellites are nearby, then if you plot these circles for all the four or uncertainty range, instead of giving a point, it will give us an area with some length and width. So uncertainty will be very high in this case, like this much. So if the satellite spread is more, then the positioning is accurate. If it is less, then positioning is having uncertainty. And how we define this GDOP is like 1 upon volume of this cone which it is making with this four satellite. So 1 upon volume. So if you have spread, like all the satellite, if they are having spread very high, then this volume will become very high. And if it will volume will become high, then this factor 1 by v will become less. And that's why lesser the DOP value, higher the positional accuracy. And this thing, once we solve these equations of this satellites, then I told you in the beginning of the class, we will end up with the solution such as delta x is equal to b transpose b minus 1 b transpose delta p. So in this term here, b transpose b inverse will define this DOP terms or DOP formulas. So if you consider x, y, z and t, then it's a geometric dilution of precision. If you just take the positional parameter, which is X, Y, and Z, then it is a positional dilution of precision. If you take X and Y, then it's a horizontal dilution of precision. If you take V, then it's a vertical dilution of precision. And if you take T, then it's a time dilution of precision. And when you do the GPS planning before going to survey, you can use Trimble site or some other site for survey planning. And there you will get to know what is a different DOP values at a given location and given time. So what you have to do is you have to give the location where you want to do survey and at which time you want to do survey. So here you can see time throughout the day, how many number of satellites are available, how many of are available from GPS, GLONASS, Galileo, BeiDou, and QZSS. And you can see the DOP value considering all the satellites. So here you can see it's lesser than at given time, it's lesser than 2. And it is very excellent DOP value when we do the GDOP value, like GPS survey. So consider in mind lesser the value, good the positional accuracy as the satellite spread is high. Any doubt in this concept of DOP? Okay, if there is no question, we'll move forward. How many Navstar satellite GPS satellites in standard constellations are operational and provide uninterrupted service? So we need 24 satellites. 24 satellites. Okay. Yeah, I think it's 36. Yeah, it's 36, but some of it is not working. So uh, we have to give it like if we take normal system, then 24 are necessary. So operational 24. If someone is not working, in that case, it is use the data of additional satellite. But here we'll go with the 24. It will change with the time to time because we don't know that which is operational, but to get with this number, we'll take the minimum number which is required for uninterrupted service. But this question is like depending on the actual situation, it answer can vary, like depending on the real life data. So which of the following factors is or are responsible for ionospheric delay, which is coming from the atmosphere in GNSS observations? So ionosphere is like where lots of electrons are there and charged particles are there. So that is the first thing. It is coming because of that. Another thing is the carrier frequency are also important. If you have single carrier, then it will introduce a lot of ionospheric delay. But in the same way, if you have dual frequency receiver, it will reduce the ionospheric delay. So those two are correct. Size of GPS receiver will not affect, and size and accuracy of atomic clock will also not affect here. Next question is, which of the following statement is or are correct in context of GPS data collection method? So this course can be used, this continuous operating reference system can be used as a reference based GPS receiver. So like we discussed this in just a few time ago. So that option is correct. A reference or base receiver should record the observation for a longer period as compared to the remote station or rover station. So that is also true. Base will collect info like data for long time and then it will find out the error using that data. The next option is remote rover, remote or rover GPS receiver must always placed on a known location. So that is wrong. We fixed base as a known location and rover as a unknown location. Reference and remote GPS receiver must be placed on top of each other. So that is also wrong. Not it's like away from each other. That's why we can access the area. The next question is, which of the following error are corrected in DGPS? So error is which is common. So tropospheric delay, then we have orbital error and ionospheric error. Ambiguity in atomic clock, which we cannot do because receiver clocks can vary from each other. The next question is, which of the following statement is or are correct? Triangulation is preferred in plain areas. So that is wrong. Triangulation is preferred in hilly areas, whereas trilateration in plain areas. So the difference between these two is that in triangulation we measure the angle as the name is given if the three angles is known, and trilateration we measure the sides of the triangle. So the sides are known to us. So in triangulation the angles are measured with great accuracy, while in trilateration sides are measured with great accuracy. So option C is correct. Next is in absolute positioning method, the SPS users can get the accuracy of, so this is a standard positioning system. We get the accuracy of around 80 to 100 meter in this case. Which source of GPS error in standard positioning system can have more than 1 meter error? Any guess here? So satellite error, which is around 5 to 7 meter. And then we have ionospheric error, which is also zero point 0.7 to 1.2 meter. Other errors are very small in nature. Multipath error is maximum for CA code. We discussed this in PPT. Uh, how many types of observables are present? So two observables, code pseudo range and phase pseudo range. One, we find the distance using delta t, and in another one, we find distance using phase difference. Filling the blank is an additional error associated with the carrier phase pseudo range. So in carrier, we have cycle sleep error, which is somehow we just like cycle sleep is some object is coming and just the change in the like how we record the signals. So it just go down or go up. Then we have integer ambiguity. So it's like error in calculating the phase, which is go with the phase operations where we have pseudo range, where this is the cycle sleep is associated with the number of cycle, which is where we do the carrier based calculations or frequency based calculations. So, and the other two are atmospheric error, so that are not the correct answer. So correct answer here is cycle sleep. Then the next one is during the GPS observation, DOP value should be minimum. Next one is the most systematic error in GPS observable is, so which error we can model very easily. So cycle sleep is very difficult because we don't know the source of cycle sleep or when it came. So thing here is receiver clock error or any clock error is easily detectable because we know at which time satellite is giving the data and what is error associated with the receiver clock. So that can be like calculated easily compared to other because we don't know how much ions are present in the atmosphere or what is causing the integer ambiguity or cycle sleep. So that parameter we don't know, but receiver we are in direct contact and we know what the error might come from, so we can model it proper. Then the next is ionospheric error is minimum for, so that is for L. Ionospheric is less for L2C and L1 code basically. So C code will have very less frequency and which is easily get affected by ionospheric. A parameter for computation of satellite vehicles position is obtained from satellite vehicles position. So the X and Y of satellite, it will obtained using navigation data, which GPS satellites are sending to us. So in GPS survey, the point positioning method, so it's a long-term average at point positioning because it means we are going at one location and we are creating multiple points and we are taking difference of it and we are just putting the point only. So option A, B and C are correct and we get more like not that good error in static point positioning. The next is SPS mode which produce the less than 1 meter error. So here tropospheric and orbital error can Great. Like as we just discussed in the other question, which is having more than 1 meter error. So this is the opposite question, which are having less than 1 meter error. Then which of the pair is correct? So PDOP is positional dilution of precision, GDOP is geometric dilution, HDOP is horizontal dilution precision, and T is for time, not for the total. What is smart station? So smart station is the integration of GPS as well as total station. So option B. So how it is useful? Let's say we are collecting data through GPS and we went to some tunnel or some area in jungle. So in that case, we will stop receiving the signal. So during that time, we will use total station. When we can see the point easily, we'll use total station. But when we are going away, we can use GPS. So like that, it will complement each other and we can do the survey. In the context of global navigational satellite system positioning, the Sasta-Mounian model provides a correction for. So this model is how we can remove the systematic error, and this model is particularly used for tropospheric error. So if you read detail about books, you will get to know this tropospheric delay is caused by the moisture and gases present in the troposphere, and that we can use like remove or model it using this Sasta-Mounian model. So that was like questions from GPS side. Some questions which we solved as a direct part of the lecture notes on NPTEL. And for answer of some of the questions, you might have to go deep down into some books and have to read about more about the different types of error and then mathematics associated with that. So if you are interested in knowing more about GPS, there are a couple of courses in NPTEL as well, such as your GPS surveying course is also there. So you can go through those courses. Uh, do you have any other questions, feedback, like how we are conducting these sessions, how we can improve it? Then please let me know. Yes, it is available. Yeah, if you every week these assignments will come, so you do not have to attend the videos in this doubt session. You can just give the assignments, solve the assignments, and give the exam. This sessions are for if you are not able to solve the assignments. So this is for that. But yeah, you can if like every week they will upload the content. Not everything is uploaded at once. So yes, yes, yeah, no, no, it's not available like that. No, yes. So if you are interested in that, there is a other like the recorded lectures are there for GPS surveying course by JNK. Yes. So next week we are going to learn about LIDAR survey. This is the next week contents. So we see some of the data, how we can process the data of LIDAR, and how we can solve the different like this kind of question answer of LIDAR, and then some of the data processing in QGIS, how LIDAR data looks and how we can process it. Okay. So that's it for today's session. Thank you everyone for joining. Hope you enjoyed this session. Okay. Thank you. Bye bye. Next day.